Well, before we get into any really new material, let's review a few things that we had covered earlier before break. It's been, well, 2 weeks since you probably looked at any of this stuff. So let's take a look at the voltage drop across a resistor again and provide a few more details and maybe the formalism that we're going to need a little bit later. Yeah. So ultimately, we're going to need to relook at the voltage drop across a resistor again in more detail. Uh, you obviously know we covered in lab and we talked about it in class. It's usually called Ohm's law, namely V equals IR. Uh, but I think we said even at the time that what we really have is the voltage drop across a resistor. The magnitude of it is equal to the current flowing through it times R. And I represent that symbolically here. Here's our resistor R. We've got a current flow, which I'm putting from left to right, from A to B. That may be the actual direction of current flow, or it could be maybe we didn't know what the current flow was and we just assigned this direction as sort of a guess, or then and we'll see how that transpires in subsequent lectures. But for right now, let's just look at this situation and look at what I mean. If I really spell this out, I want the voltage drop across that resistor as I go from A to B. So I'm going to be going from left to right, and that really specifies it here. And remember, the delta is always the final minus the initial. So by the time I've gone across this, the final potential really is V sub B, and the initial potential was the potential at A, which is V sub A. However, we know that charges, positive charges, and remember we've got a current here that has positive charge delta Q that's flowing in this direction, and positive charge always moves naturally from high potential to low potential. And so in this particular situation, I know if the current's flowing this direction, that the potential at B is less than the potential at A. It flows from high potential at A to a lower potential at B, and so VB, the potential at B, has to be less than A. And really then we can write in more detail, more precisely, that the potential difference from A to B is really a drop, and that's why I usually refer to it as a potential drop across a resistor. And if it's a drop, that means the potential at at B is smaller than A, and so this quantity here, the magnitude of it is I times R, but VB is lower than VA, and so it becomes a negative number here. Note this in this notation, we could also do the potential difference if I maybe wanted to get the potential difference as I went from B to A, going from right to left, to get the potential difference across that. And that I would probably write delta V as I go from B to A, and that's the final minus the initial, VA minus VB. And pretty clearly, if I go from a low to a high, the difference I'm going to increase by this amount. So delta VBA, B to A is a positive IR. So it kind of depends on which way you're going across a resistor, whether it's a plus or a minus. And what I like to do is the following. If I have a resistor, A to B, connected between points A and B, and I got a current flow, or somebody tells me the current's flowing in that direction, or I've essentially assigned that as the direction of positive current flow across that resistor R, then based on that current flow direction, I assign a polarity to that resistor, and I usually indicate that with a little plus sign on the high side. Remember, current naturally flows from high potential to low potential, and so the high potential side of the resistor, based on the direction that I is going, I assign as positive, and I put a little minus sign on the low potential side. And we'll use that convention. And then the voltage difference across that resistor R is either going to be plus or minus I times R. Magnitude of I, magnitude of R, plus or minus. And then we use this rule. Use the last sign hit as you move across the resistor. So if I'm going from A to B, then the last sign I hit is the negative sign. And so this plus or minus, I choose the negative sign, and the potential difference as I go from A to B is minus IR. Alternatively, if I were going from B to A and wanted the potential difference as I moved across this from B to A, well, again, I write down the potential drop across the resistor, plus or minus IR. And then as I move across it in the direction that I want to, I use the last sign hit, in this case the positive sign. And so the potential difference across that resistor as I go from B to A is plus IR. Well, it'll be convenient a little later on to use this methodology in which we mark the polarity of the two sides based on the direction of positive current flow. This part of the lecture will relook at the EMF, or electromotive force. And if you remember, I think this is more or less where we left off before we went on spring break, or extended spring break, which I hope everybody enjoyed. The electromotive force is, again, one of the most horribly named concepts in probably all of physics. Uh, it's the EMF is from the electric, and the motive is the motion, and force is the F. And the EMF, as I think I probably told you then, at least I usually do, it turns out that it's non-electrical in nature, and it's not even a force, doesn't have the same units as force even. But I guess it does have something to do with motion of charges through a battery anyway. Yeah. So let's review that. Again, I think this is, if I mark my notes right, this is where we left off before we went on our sort of extended spring break. So EMF. A lot of times they'll talk about these as DC power supplies. Okay? DC is direct current, but essentially a DC power supply is any voltage source that maintains a constant potential difference across its two ends called its terminals. And I'm sure you've seen these in the laboratory already, but we'll be looking really at any DC power supply. All that's required is a constant potential difference across its two terminals. Anyway, DC power supplies are used to produce direct currents, and remember, DC direct current is currents that flow in one direction only, so they're always going in the same direction. And as I think we've mentioned maybe several times, by our convention, positive current is positive charge that flows from the DC power supply. In this case, it's simply a battery, or what we'd typically call a battery. And as we'll see, that should probably be called a cell. And in fact, if you go and buy these, and you look on the side of the package, it'll say D cell or a C cell, AAA cell. It doesn't necessarily call them batteries, or technically they're not. They're cells. But here I've got a positive end. Remember, that's the button side on a D cell, for instance, and the negative side is the flat end. And by convention, really the current produced by this battery flows from the positive terminal, in this case through a resistor, and then back around to the negative terminal. External to the power supply, or in this case the cell, the current naturally flows from high potential to low potential. Positive charges like to go from high potential. This positive terminal on the battery is not only positive charge, it's the high potential side. the negative terminal on a battery is not only the negatively charged terminal, but also is the low potential side. So here we have current flowing in this direction, at least external to the battery. Okay? The current actually makes a complete circuit, so even inside the battery there's current flowing through the cell in this case, or the power supply if we were looking at a different kind of DC power supply. We can use what was covered in the last lecture and mark immediately, once I've got this current flow direction, I can mark the high and the low side of that across that resistor. These lines, of course, are wires, and those you always assume that there's no potential drop. They're sort of ideal wires. Every wire has some minuscule potential drop across it. If it's a very, very long wire, you can actually measure it. I think you probably did some of that in laboratories as well. But for the sake of circuit diagrams that we'll begin to draw, anytime you see a line, it's a wire, electrical wire, in which there's no potential drop. The only potential drop external to the battery anyway is right here at that external resistance R. Inside the battery, something different happens. If you look at the current outside the battery, the charges actually move from high potential down to low potential. But inside the battery, the current has to flow through the cell. Here, we're picking up some positive charge. There's a little piece of positive charge at this end, and it has to be moved across to get back over to here. If it all piled up, it would eventually use everything up. So the current flow is in this direction, but that's not the natural direction positive charges like to move. Positive charges would like to move from positive to negative, not a positive charge picked up here and moved over to this side of the battery. The battery has an electric field. Electric field, remember, is always from positive high potential to low potential. And so there's an electrical force that's pulling this thing this direction. And so for me to move a piece of positive charge over to this side, I have to apply essentially a non-electrical force to oppose the electrical force to move it over to the other side. And that really is where the definition of electromagnetic force comes from. Usually represented by script E. Sometimes people will use a capital V here, but we're already using V for potential, and we're using the potential difference and other things. So usually I'll try to use E for EMF if that's a source of electrical voltage for us. But technically the definition of the EMF, E, is the non-electrical work done on delta Q inside the cell to move it from, well, that should be negative to positive.